Today we're going to be focusing on discrete probability spaces, and we'll continue that later by discussing continuous probability distributions. Just as a refresher, recall that probability distributions are over some event space, and the probability distribution for discrete event spaces assigns a probability to each event in the outcome space. Examples of these are things like coin flips or rolling a die. Recall that probabilities have to sum to 1, and each probability has to be greater than or equal to 0. It's also worthwhile to refresh some mathematical conventions. So recall that a factorial is all of the numbers, including that number, multiplied together. So if you have 3 factorial, that's 3 times 2 times 1, and so that's a total of 6. And if you have 9 factorial, that's 362,880. And if you have 0 factorial, we're going to assume that that is 1. Similarly, we're going to assume that if you raise some number to the 0th power, we're going to assume that that's 0. And that makes sense if you think about what happens on either side of it. If you have 3 to the negative 1, that makes sense to be 1 over 3. If you have 3 squared, that makes sense to be 9. And so 3 to the 0 makes sense to be 1 because that's multiplying 3 by itself not at all, and if you have no other things in a multiplication, that's 1. There are many kinds of discrete distributions, and we're just going to talk about some of them today. What's also an important part of our discussion is the notion of parameters. And so parameters tell you what a distribution is like. And so these are the numbers or vectors that tell you what your distribution is. So this will be very important to our discussion going forward. Distributions are defined by parameters. And so even though we'll talk about families of distributions, any particular distribution has a single set of parameters, and we'll see that in concrete detail in just a few seconds. Today we'll be talking about distributions abstractly. We won't be going into what they're useful for, other than describing some class of events. But we'll see in the next couple of weeks how they're very useful for tasks like regression and clustering, and this will serve as a foundation for talking about those things rigorously. The first distribution that we'll talk about is the Bernoulli distribution. So a Bernoulli distribution is a distribution over coin flips. And this could be a fair coin flip. And so if you have a probability distribution where the two sides have equal probability, that is a Bernoulli distribution with parameter 0.5. And you can also have unfair coin flips as well. So if you were to model the probability of a failure in a manufacturing process, so you have 2 outcomes, either you successfully produce a part or you don't, that too is a Bernoulli distribution, and you have 0.995 probability for success and probability 0.005 for failure. The neat thing about probability distributions is that even though it is a distribution over 2 outcomes, we only need 1 parameter to completely define this distribution. If I just told you the probability of success or the probability of failure, you can tell me what the other one is. So think about why that is for a second. Right, you don't actually need both probabilities. If you just have one, you can get the other by subtracting it from 1. By convention, typically people only give the probability of success, and that is the parameter of your Bernoulli distribution. The Bernoulli distribution is really simple, and so you can just write it down with a single parameter, but we'll be talking about functions that describe distributions for many of the other distributions that we talk about today and for the rest of the course. So let's introduce what it means to write down a function that describes your distribution. So what we want to do is we want to have a function that takes a particular outcome and gives us the probability of that outcome. The function that does this is called a probability mass function. And so this takes some input x and assigns a probability to that. So this gives us a probability for an event. One way of doing this is having a function that's split into 2 parts. Are you asking about success or are you asking about failure? If you're asking about success, I give you the probability of success. If you're asking about failure, then I give you 1 minus the probability of success, since we defined the Bernoulli probability with a single parameter, the probability of success. Okay, we can make this even simpler, and so mathematically we often strive to have the simplest equation possible. We don't need to have an if statement in there, we can just write it down as a single function. So let's take the probability of success and represent it by a symbol theta. And so this is just the probability of a success, and that becomes the parameter of this distribution. And if we want to have a single function that describes what it means for an event to take on a particular probability, no matter whether that event outcome is a success or a failure, we can plug that into an equation. So we just have a single x that comes in, and whether that x means success, 1, or failure, 0, we can assign it the correct probability. And we can do that by taking the parameter for success and raising it to x multiplied by 1 minus the probability of success, 1 minus the parameter of the Bernoulli distribution, and raising that to the 1 minus x power. So this is where our definition of anything raised to the 0th power being 1 comes in handy. Okay, so let's think about that a little more carefully. Let's say that x is 0. If x is 0, then this part goes away. It becomes 1. Right? Because x was 0, and anything raised to the 0th power becomes 1, and so now we only pay attention to this part. And if x is 0, then we can forget about this exponent as well, because that becomes 1, and anything raised to the 1th power stays the way it is. So then we just have 1 minus theta, which is the probability of a failure. And if x is 0, that means we're asking about the probability of a failure. So everything worked out the way that we wanted it to. Okay, so it works for x equals 0, or failure. What if x is 1? So if x is 1, then the second term goes away by the same argument. So 1 minus 1 is 0. So anything raised to the 0th power is 1. So the second term goes away because 1 minus 1 is 0. And then we're left with the probability of success raised to the 1th power, and that just gives us a probability of success. So everything worked out as intended.